Val? Faré una mica d'introducció biogràfica en anglès i després ja donarem lloc a la xerrada que us presentarà la xerrada Wave Energy Assessment from High Resolution Satellite Altimetry and In situ data for the Mediterranean case. Val? Llavors, so Sonia is a dedicated Earth science scientist with over more than 20 years of experience in wind waves. So her field of expertise is related to the wind and the influence of the wind and waves of the ocean. She has various international projects in the International Space Science Institute and multi-wave rock waves, Sirocco, etc. And he has a PI on some European projects funded by the European Commission and the European Space Agency. In particular, the last one is the one that some results will be presented today, which is the WAPOSAL proposal project. She has been awarded by the Juan de la Cierva and Torres de Quevedo grants, and a grant also from Portuguese Science Foundation. She has worked in different places. He has an extensive international experience in different research centers, which include the University of Dublin, Instituto Superior Técnico de Lisboa, also NTNU in Norway, IMEDEA, and UPC in Spain. And also in the Federal University of Rio Grande in Brazil. She has obtained the master's degree in CITESE in Mexico and the PhD in University of Lisbon, right, in Portugal. So in recent years, she has focused in the research of extreme waves, wave current interactions, and remote sensing of the ocean wave modeling and cyclones and renewable energy. So particularly some of the aspects that she will explore, she will explain today, it's how to relate also the wave potential and also related to the wave energy extraction. And so he collaborates for the European Space Agency, and also it's part and programs of the Earth Observation Science application from Climate Department, where she assessed wave project using high resolution altimetry products, which is part of the talk that she will explain now. So thank you very much, Sonia, and please, the floor is yours.
Thank you, Jordi, for the presentation, and thank you for being here today. As you know, we are facing energy crisis, and each of us should contribute somehow in order to help to find a solution regarding this issue that we face. So today I will present some results from the WAPOSAL project. The WAPOSAL project was closed recently. It is an application project, proof of concept. And as you see, I have some colleagues also. So why wave energy matters? Well, there are millions of people currently lack access to electricity, and about the 40% of the global population live within the 100 kilometers of a coast. And we have to provide people with access to electricity near their houses, as for example in the African coastal zones. And well, all of supporting this idea. So there exist some pilot projects, as for example Jet Techno, which is designing floating devices. I would like to make a comment here, because I know that at ICN is a big group of ecologists. I consider myself also ecologist. We don't want with this project to install devices affecting environment. We only are tried with this project to add more information to solve this situation of the energy crisis. So also we have in Spain, in the Basque Country, the Mutrico oscillating water column plant, which was one of the first one in being operational in Europe, the wave pilot in Portugal, in Cabo Peniche, and the Eco Power also in Cabo Peniche, in Portugal. And there exist some types of wave energy converters. I only brought here 2 examples. The attenuators are floating structures that by flexing and bending with the wave motion, they can convert this wave energy into electricity, sending it to grids in the coast. So also there are the oscillating water columns that by compressing air in a chamber, like for example the case of Mutrico that is shown here. Mutrico here. So by pressing the water column that fall inside of a chamber, the wave energy is converted into electricity. So I brought these examples because they are the, how to say, for example, the jet techno is a floating structure like a ship that travels over the surface, the sea surface, to the place where the waves are. And from there, they convert they transmit this energy to the coast, to the grid. So here is the case of the Portugal. This is a structure that exists in the coast. And here is the example of the Pelamis that is very useful for being installed in deep waters, like for example, in overseas territories, like for example, Azores Archipelago. This is an example of how this work, this mechanism works, taking into account Mutrico's example. So by pressing this water column, it is converted into electricity. So, but this is only about devices, but there are challenges and facts, like for example, lack of wave data, lack of studies considering climatic scenarios that are needed for the wave energy converters design, high cost of maintaining these devices, lack of studies focusing on the wave variability. Variability is a very important factor, it's a cost driver when you treat this kind of subjects for the design of the devices. So power matrices also are based in all information, and beside of that, wave energy is more reliable and persistent resource than solar and wind, that for some reason many institutions are trying to install everywhere, in particular the windmills. So in this context, Guaposal project had the primary objective of establish or the creation of a particular database containing the information on the wave power density along many coasts. So the project aimed in developing an innovative digital tool that uses air observation data to create this kind of a state-of-the-art database. So the main outcomes of the project are the mapping of the wave energy resource, different characteristics, like for example, variability trends, average maps in different coastal zones, and identify also and suggest the best or the ideal locations for the wave energy extraction. So there are some previous work done during my stay in NISA as visiting scientist, and the Guaposal was developed for different regions shown here in these pictures, including far territories like, for example, the French Polynesia, the Azores Islands, the French Guyana, and where the no in situ data are available. So what we did was we used data from a previous European Commission project where we created a database. This database consists of basically two main missions, Cryosat-2 and Sentinel-3A and B, that were reprocessed with a special program called Algorithm Samosa Plus. I will explain what it does. So we also used about 82 real wave buoys and 42 ERA5 virtual stations. So here we chose the goodness of the data we used in the assessment of the wave power is basically that the data are spaced at every 300 meters between two estimates. And this is a very different product. It is named high resolution altimetry data. And in this picture, you can see that when the satellite pass nearby coast, the signal is corrupted. And because of that, nearby the coast, all these estimates cannot be used, need to be not considered. So here we compare two different data sets. In red are the official version distributed by EUMETSAT of Sentinel-3, and in black stars we represent the same data but reprocessed with the algorithm Samosa Plus. As you can see above the green line, which is the flag for the quality of our data, above this data are many red crosses indicating that they are not valid. And when we reprocess this data with the Samosa Plus algorithm, you see that we get more valid estimates nearby coast. This distance embraces 5 kilometers from coast. So this is a good tool. Also, for your information, I can say you that EUMETSAT now have a global product of Sentinel-3, and also is going to distribute the Sentinel-6, reprocessed with the Samosa Plus algorithm. And I am not sure if this is available already in open access for all now, but perhaps if not, it will be soon. So this is the flow chart of the work performed in the frame of the Guaposal project. We retrieve the OCRE-IO database, altimetry data, and wave buoys and ocean currents. Then we compute regression coefficients, and I will explain why. And in order to estimate the along track wave period, then we estimate the along track wave power density and its trends. And finally, we also estimated some coefficients of variability. And then we also explored what is the influence of ocean current on the wave power density. And finally, we construct some average maps. So this is a schematic representation of the method we use. For a certain region, we estimate, as I said, empirical wave period estimation, and then we can estimate or compute all these different characteristics of the wave power density. So for those that are not familiar with the wave power density, I will show what is this. So this is a simple formula that we use for the estimation of the wave power density, where the missing variable is the wave period. So when we use satellite altimetry data, we usually don't have this variable, but it can be estimated, with exception of the CIFOSAT mission that already provide the wave period, but the time series is short. But we use the CIFOSAT period in order to tune our method, and we obtain very good results. So this is an example, a schematic example of what is the wave power density. This is a measure of the amount of wave energy that flows through a unit of wave crest that is marked from crest to crest. In these arrows, I represented the wave propagation direction, and from this equation, you can see that the wave power density have a quadratic dependence on the significant wave height. So using satellite data, as I said, we can have the significant wave height, but not the wave period. So we have to estimate it. And for that, we used a method that was proposed in this work that, in our case, as I said, is already a tuned method. So we form the part of x, the quantity x, and the zero crossing wave period in order to collocate the satellite data with the wave buoys. In this way, we can estimate the coefficient, the regression coefficient A and B, and we can have the missing variable, the wave period. So here you have a comparison for two different locations. One is located in Greece, and the other is in Spain, in Cabo de Palos. And as you can see, for the wave period, the correlation is less good than for the significant wave height in both locations. And I will present now the result for the Mediterranean Sea. So in this picture, you can see that the distribution of the wave buoys is not very uniform in the Mediterranean Sea. The wave buoys, unfortunately, are distributed along many countries that are rich. But in the case of the African continent, we don't have any buoy, with exception of one or two that should be here but are not in the coast of Israel. So because we are interested to provide information to along coast to poor countries, we retrieve from ERA5 reanalysis, and we call them virtual stations in order to estimate the wave power density in those places along the Mediterranean Sea where we don't have any in situ data. And here is the comparison in both locations. In location 8, using ERA5 data, and in location of a wave buoy from the Greek wave buoy network. And as you can see, using the wave buoys, of course, the correlation is higher, but in general, the comparison shows that ERA5 can be used in order to perform this kind of assessment. In the case of the wave period, we also the statistic shows similar results. So ERA5 is a good candidate as well. Here we compare some statistical metrics between the both missions, and as you can see, the bias resulted similar at each of the wave buoys distributed along the Mediterranean Sea. The correlation coefficient also, with some exception of this wave buoy, and the scatter index in the bottom panel also resulted similar. Here we already are speaking about the variability, and for that we follow this work in order to estimate the coefficient of variability following this formulation and the seasonal variability index. And as you can see, this is an example along this. Here we have the numbers of the locations. And in red, I marked the highest average wave power density at this location. And in blue, we can see only 2 stations that has low variability, and above of this red line, which is the threshold, are considered with a high variability locations. Anyway, I can say that variability is a very important factor, and because the Mediterranean Sea is characterized by a high variability in some places, so our project provided this information for the 11 regions shown at the beginning of the presentation, and it is to allowing this characteristic of the wave power density, we can recommend the ideal places. As I said, we also investigated only using satellite altimetry data. Is not possible to get inside of these complex phenomena of the wave current interactions. I believe that this need more data, like, for example, high-resolution simulations nearby coast, and also more and more data. So here you have an example of a comparison performed along track between the wave power density represented here and the current speed. So as you can see, the correlation coefficient of these quantities is high, but this never doesn't happen always. It is seldom because it depends on several environmental conditions and many factors. So we represented here a long track that unfortunately is in the border, is not seen very good. In the color scale, we represented the wave power density, and here we get from era 5 the wave height and the wave propagation duration with arrows, and here the wind field. Also, this is another example where the track is seen better than before, and as you can see, the highest magnitude of the current coincide with the highest values of the wave power density. Usually, when we have wave and currents traveling in the same direction, coming to the same place, then we have a high wave power density. But here also I need to comment that having a huge wave energy from the ocean is not the best condition for installing something or a device to retrieve the wave energy into electricity, because if the wave energy is too high, the device could be damaged. So there is a balance between an intermediate wave energy intensity, and the variability of the wave resource should be also not very high, because if you have a lot of variability, you cannot predict anything. You cannot understand what will happen tomorrow. So this is something to consider. So coming to the WAPOSAL mapping, we constructed the along track average wave power density using the Sentinel-3 A and B data. We see that the maximum value is in the Western Mediterranean Sea, associated with the Tramontana and Mistral events, but also we see that there are some spots here along the basin. We compare our results with a published paper from the Greek Institute, based in 30-year simulation using the one model and spectral wave models, and we see similar patterns. The highest values are related with the Tramontana and Mistral. And here we show that the Guaposal average map using both missions. And we see that the maximum values correspond to the maximum values here in regarding these simulations. So we also performed a seasonal analysis using the along track information. Separately, here are the average maps, and also we compare with the same paper. And the results are really very encouraging. So, as I said, we are interested in to know or in to provide crucial information for poor countries. So here I mark it with different circles and colors along the African coast, these locations. So we expect that, of course, because of the Tramontana and Mistral, this location will have the highest energy potential, but we are not interested in that. So we are interested to know and to provide this information to this part of the basin. So here I am showing the local distribution of the annual wave energy potential. And as you can see, location 16 is depicting a high values, and location 21 an medium wave energy potential. So if we go back and we analyze the reason of that, this one is in a sheltered zone, and this one is facing the fetch is largest, and for this reason it has an ideal conditions regarding the intensity of the wave power density. And here we have a low value because it's in the Gibraltar Strait, and of course is more protected place or sheltered. So coming back to this picture, we can see that these diagrams are showing a high variability and also a kind of bimodal distribution related with the wind, sea, and swell. So I put it here, a kind of legend about that. And well, the conclusions are listed here. So we estimated the along track wave period, and we applied a method that works pretty well. And we did this job for 11 different regions. And the method was verified using wave buoys and ERA5 data. And a relationship between ocean currents and wave power density is shown, but it deserves more attention and a deeper analysis. And finally, the Guaposal project identified the best location and submitted to ESA this information. So after all, the outcomes of the Guaposal project are large because we built a lot of collaboration with the Ocean Energy Research Center of Ireland, with EOMAP, FUGRO in Germany, and many others institutes in Spain and Portugal. And we already submitted two papers, or one of those will be submitted next week. And we are working in 2 more. So finally, the Guaposal database is published in the ESA's repository, and it looks like this, if someone wants to have a look. So, well, this is the acknowledgement and future actions. Well, as future actions, I suggest to apply to other poles, of course, and to incorporate a multidisciplinary, different, aspects, like, for example, high resolution simulations, use more satellite missions, like, for example, the latest that has a very good resolution. and perform a global map of the wave power density, and also make use of the artificial intelligence in order to be able to predict the future of the wave power density. So thank you for your attention. These are Andres and Maria, my team, and that's it. Thank you. I wait for your answer. If someone have questions, I am available. Yes, Giovanni.
It's really not my field, so I'm here more to understand. When you calculate the wave power, what period do you use? Mean, peak period? Is there a standard?
Well, usually, in order to estimate the regression coefficient using this method that we applied, some wave buoys don't provide all the wave periods. So basically, we look at for the zero crossing period, but sometimes it was not available. So in that time, we used what we had there, that could be the mean period or at last peak period. Yes.
And direction doesn't matter?
No, at this point we don't work with directions, and because with satellite altimetry data we don't have this data. But this is why I suggest to extend this activity, incorporating other different tools, like, for example, high-resolution numerical simulations, and get the wave directions, of course, is important.
What's the increase in data resolution when you use something like SWOT?
Well, with SWOT, I don't remember exactly, but the resolution is pretty good nearby coast and everywhere. And now a lot of good results and new features are being discovered thanks to the Rolls Royce that is the SWOT. It's a Rolls Royce. And of course, this is the main handicap is the time series that is short. But with time, it will be very good and very helpful.
On the microphone, otherwise I keep going.
I think I can ask a question too. This is a little bit maybe off-field, but you've got some future plans. So if it's not being considered, maybe you can consider that in the future as you submit new proposals and applications. And that's the economics of these kind of plants. And in particular, I would so like the question is the one that you mentioned in Motrico, that it's been operating there already for a decade and a half, 15 years now. It'll be interesting to know what's the cost of the energy to build the plant and balance that against the amount of energy that it has produced or generated over a decade and a half, just to determine whether the economics of the whole process of building, in this case, oscillating plant, right, are worth, or how they can be improved or they can be tailored.
Yes, this is a good point. Of course, this is an industry subject, and I don't have this information. But your point is interesting. Why we could invest in the construction of these in devices or structures along coast if they are compensated taking into account the main goal of this construction. Yes, of course. We cannot decide this. I think so, no, but yes, of course. Our idea with this project was only the creation of the database, but we are aware about the limitation that this database has. It's only based in 2 missions, reprocessed with an special algorithm, having a very high resolution nearby coast. And well, this is why this should be extended. Yes, of course, incorporating more missions, more satellites, and more different way of analyzing everything.
Any more questions? Shall we want to add something? Or do you want to add something else?
No, from my side, it's okay.
Okay, so thank you.
Thank you to you.